Well, this expression can be written as a real column vector plus I times another real column vector. In other words, then you're going to have a real part plus an imaginary part. Now, without looking at this, how do you split this into a real part and an imaginary part? Well, you should understand that. You should think about it, and hopefully you did in class. It's very simple. You just write the real part here as a column vector, this factor and or this term and this term as a column vector, and then I times the column vector consisting of this term plus this term, without the I, because of course the I distributes through. So you can understand that if we write it like this, clearly this is going to add up to this. Okay? Well, the payoff is we now have two solutions to our system. Okay? And those solutions turn out to be linearly independent. Now, how do we have two solutions? Well, as we know, the real part of our solution is itself a solution to the system. So if I plug y1 equals e to the t cosine square root of 2t, and y2 equals negative 2 square root of 2 over 2 e to the t sine of the square root of 2t, take this vector alone, let that be y1. Okay? So I'm saying, okay, let y1 equal this vector. That alone, plugged into your matrix equation, or plug, okay, now we get into little notation. I need a big fancy y, but that's okay. Plug this in for y1, plug this in for y2, the scalar function y1, the scalar function y2. This is a vector function. Okay? If we plug, let scalar y1 equal this, scalar y2 equal this, we're going to have a solution to our original equation. And since it's easy to put that up here, that is, we plug those functions in for this y1 and this y2. The first column, or the first row for y1, second row for y2. We have a solution to the equation. You can check that out. Well, we can also get that if we do this solution. This is our y1 and this is our y2 function. Okay? Now, I need to do a little bit of modification of my notation here, because here's, there's a little confusion about notation that arises here. And this is where I do a big fancy y. So I'm going to call this big fancy y1, and I'm going to call this big fancy y2, to make sure we don't confuse it with the y1 and y2 that we get here. Okay, so from this column, we get y1 equals e to the t cosine square root of 2t. And y2 equals negative square root of 2 over 2 e to the t sine of the square root of 2t. Hopefully those are legible. But, we get a little y1 and a little y2. These are vector functions, y1 and y2. Each vector function has a y1, y2 vector. And in other situations, we've actually called this y11 and y12 for the y1 vector. So we might call this y11, y12. And we've done this in the past. So I'm going to say, okay, y11, y12. If we let this be y1, this be y2, it satisfies our original equation. And over here, we're going to let this be like y21, y22. So here we have y21 equals e to the t sine square root of 2t, and y22 equals square root of 2 over 2 e to the t cosine square root of 2t. Need some parentheses and it gets all messy. Okay, those come out of here. So this would be like y11, y12, and this would be like y21, y22. So big fancy y1 has a y1 and a y2 that we call y11 and y12. Big fancy y2 has a y1 and a y2, we call them y21 and y22, so we can distinguish these vectors. Okay? Well, this is a solution, this is a solution. You can check the Wronskian. I actually tell you to do that. This is our, we're going to call this big fancy y1, big fancy y2. Okay? The y1 vector, the y2 vector. This is a fundamental set. And you can verify that the Wronskian is not equal to 0. I think the Wronskian comes out, it looks pretty obvious, comes out square root of 2 over 2 e to the t. If you set this up in the Wronskian, the Wronskian of our fundamental set is going to be our y11, y12, y21, y22. Actually, I've kind of got my subscripts. Those should be columns. I probably should have called that y11 and y21. That should have been y21, that should have been y12. So y21, y12. Okay, don't worry too much about this labeling, but I'm gonna fix it in a minute and just show it to you in another video. Labeled correctly, I got a little careless there. So that this column is one solution, this column will be this solution, and this column will be this solution. Okay, so I'm gonna have to change that to 2-1, I'm gonna have to change that to a 1-2. But the notation will come out. Anyhow, if you do this, your Wronskian will just be, well, it's the determinant of this, so I should put absolute value signs around it. Sorry, I'm being a little careless here, but the determinant is going to be this column and this column. If you multiply this way, you're multiplying this by this. If you multiply this way, you're multiplying this by this. If you multiply this by this, you get a square root of 2 over 2. You get an e to the 2t, and when I said it was e to the t, that wasn't quite right. That should have been e to the 2t. See, I had question marks around that. I knew I'd mess up something. Okay, you're going to get an e to the 2t times the cosine squared out of this, and then it's going to be minus this diagonal. Well, this diagonal already has a minus in it, so it's going to end up positive. It's going to be this times this. Well, this times, but yeah, okay. This times this will be this times this, and it's going to be minus that. So you're going to have a square root of 2 over 2 e to the t on both, e to the 2t on both diagonals, and one's going to have a cosine squared, the other's going to have a sine squared of the same argument, and that's going to just factor out the square root of 2 over 2 e to the 2t, and you have sine squared plus cosine squared, same argument, you have 1, and you get this. So you can easily verify that the Wronskian is this. Not what I originally wrote. You have to have an e to the 2t there. Okay? Now, I say, this solution is, to be consistent, going to be our big fancy y1 plus our big fancy y2. It's a linear combination of the fundamental set. It's just 1 times y1 plus I times y2. Linear combination over the complex numbers. Now I'm going to come back and straighten out this notation. Again, I apologize for being a little careless with it, but I'll re-explain it very briefly and see why we label the subscripts the way I'm going to label them.